Logarithms. Logarithms come in the following form. So some function log base b of x. So we have our input variable x, the word log standing for logarithm, and there's a subscript that indicates the base of our logarithm. Now these are inverses of exponentials. In a previous video, we discussed how to find an inverse of a function algebraically. So let's say we take the most basic exponential function with an initial value of 1 and a base value of b, and we want to find its inverse. We know that we can swap the x and y variables and then resolve for y. But when we get into this position, we don't have the algebra tools to resolve for y, because y is in the exponent location, and moving it from there is for another course. So what we're going to do is teach the conversion between exponential and logarithmic form, and we can use that to verify the inverse. So it actually comes from the inverse, so this is kind of all related. But we can say if y equals log base b of x, and we want to go into an exponential form, the base of the logarithm and the base of the exponential are going to match. So it's log base b, so we have exponential base b. Now here's the nice thing about logarithms that can take you far in an evaluation of them, is that you should know that logarithms equal exponents of the equivalent exponential form. So if log equals y, then the exponent for my exponential is y. And what we take the log of is what the exponential equals. So this is the conversion, and this goes both ways. So if we take a exponential form and we want to go to logarithmic form, we know the bases match. We know the log equals the exponent of the exponential, and what we take the log of is what the exponential should equal, so we can make that conversion. So now when we want to finish this inverse, we do the same process, swap x and y, and from here we're just going to convert to logarithmic form. So it's going to be log base b, logs equal exponents, and there's what we had at the beginning here to verify that if this is our exponential, finding the inverse is that logarithm. And again, I know we're not using actual algebraic methods to find that, but the conversion is what we're going to use for now. So now that we know the conversion, we're going to use that conversion to evaluate some logarithms. So let's say we have log base 7 of 49. And we want to know what this equals. Well, because we don't know what it equals, we can use x as a representation for the unknown. And if we convert it over to exponential form, we'll get 7 to the x equals 49. And the value of x that makes this true is 2. Therefore, if x equals 2, then we know log base 7 of 49 is equal to 2. We'll look at a few more examples. Let's say we have log base 0.5 of 0.25. Let's say we have log of 12, or log base 12 of 1/12. We have log of 0.01. And let's say we have log base 2 of 1. So let's say these are the 4 logarithms we want to evaluate without using a calculator. Again, we can convert to exponential form. So we can say for this first one, we're going to have 0.5 base of the exponential, logs equal exponents. So again, we don't know, so let's use the unknown as the variable x, equals 0.25, or sorry, not 0.025, 0.25. Now some of you may be able to compute this as is, but my suggestion to you if you're having difficulty is oftentimes with these log evaluations, if you convert a decimal into its fraction equivalent, it's easier to recognize what the exponent is to make that equation true. So what value of x must be present for 1/2 raised to that power of x to equal 1/4, and you would find out that that value of x is 2, so this logarithm is equal to 2. Looking at the one below, converting to exponential form. What must I raise 12 to get 1/12? Well, 12 to the first is 12, So how about 12 to the negative 1 equals 1 over 12, now that we know, or we're reminded of our exponent properties with negative integer values. So we have negative 1 for this answer. Now what about log of 0.01? You notice there's no base there. When there is no base, so a log x, no base value, this is called the common logarithm. And the common log is base 10. So no base, you're going to assume it's a 10. So knowing that, if I want to solve that logarithm or figure out what it equals, 10 to the x equals 0.01. What's the value of x? Decimal again, let's convert it over to a fraction. I'm going to say that's 1 over 100. Well, 10 to the second is 100, so 10 to the negative 2 would be 1 over 100. So because x represents what this log equals in this scenario, we know that the value of this logarithm is negative 2. So remember, logs equal exponents. And maybe you're trying to notice that the question we're asking ourselves is the logarithm equals whatever power I have to raise the base to get what I'm taking the log of. So what is the power? So what is the power that I must raise the base to get what I'm taking the log of? So remember, there's technically a 10 here. What is the power I must raise the base to get what I'm taking the log of? So if you just know that that's the question you're asking yourself on a log evaluation, you don't necessarily have to convert over to the exponential form. So for the last one, what is the power I must raise 2 to get 1? Well, I must raise it to the power of 0. And in general, from this last one, we can learn that log base b of 1 is always 0, no matter what the value of b is. Now, can b be any value? Well, that's what we're going to look at next. So knowing that logs are inverses of exponentials, and we know that exponential base values have these certain constraints, the logarithm base value will have the same constraints. So in the logarithm, the base must be positive, and it must not be equal to 1. And that is because it comes from that conversion of the exponent, or exponential. It's the inverse of that. So these base value constraints are still here. If the b value is greater than 1, we're going to see logarithmic growth. And if it's between 0 and 1, we're going to see logarithmic decay. So same thing. Now, the other thing we should be aware of is what the graphs of these look like. With b to the x, where b is greater than 1, we see something like this. So this is going to be b to the x, where b is greater than 1. And knowing that the logarithm is the reflection about the line y equals x because it represents an inverse, we can figure out what log base b should look like, assuming that b is greater than 1. It will look like something like this. So this is what our logarithmic growth, and I want to make sure that this thing is always increasing to not confuse you. Now the other thing we discussed with exponentials is that they have horizontal asymptotes at 0. So we have this horizontal asymptote at y equals 0. So that horizontal asymptote also gets reflected when we try to find the inverse graph. And that is going to turn into a vertical asymptote for the logarithm. So knowing that there's a horizontal asymptote for an exponential, and through the process of reflecting over the identity function y equals x, we can see that there's going to be a vertical asymptote at x equals 0 for a logarithm. So we're going to add that in. And again, we're looking at base logarithms without any transformations done to them. So we have vertical asymptote at x equals 0, and the only way this moves is through horizontal translation. So we said the vertical asymptote comes from the horizontal asymptote, or can be found through the horizontal asymptote of the exponential. We know the horizontal asymptote of the exponential only moves through vertical translations, so you can expect that horizontal translations will move the vertical asymptote for the logarithm. So how do we identify horizontal translations with a logarithm? We're going to have log base b, and we're going to have x, and it's going to be plus or minus some value k in there. So that will indicate whether or not you're moving left or right. So you want to be on the lookout for that when identifying that vertical asymptote. Now let's define the vertical asymptote. This is new. The vertical asymptote is kind of reversing that definition of the horizontal asymptote we brought up. We say for the horizontal asymptote, as x approaches plus or minus infinity, the function approaches a constant. Well, now we're going to say as x approaches a constant, the function approaches positive infinity or negative infinity. And there is your vertical asymptote identification. So you can see from this graph that as the logarithm approaches the constant 0, so as it gets close to the y-axis, which has a constant value of 0, you can see that the graph goes towards negative infinity. Okay, so there is that fitting the definition of our vertical asymptote. And it never crosses over, so it's important that you don't cross over. So there are your properties of the log. And then let's look at an example of logarithmic decay, just so you can see the visual. Say we have our function. Let's look at exponential decay. So when our b value is between 0 and 1, logarithmic decay, knowing that it's a reflection of this over the line y equals x, is going to look something like this. So if we were to draw in y equals x right through there, we should see that reflection. This is log base b of x, where b is between 0 and 1. So this is our logarithmic decay. And up above, we had logarithmic growth. So be aware of what those visuals look like. And again, this is assuming we don't have any transformations applied to these things. These are the most basic of logarithms and exponentials, just altering the b values. So there are some properties of the graph. Vertical asymptote, something to be aware of. And we'll finish off with some domain and range. So what's the domain of my logarithm? Well, we expect it to be the range of my exponential, because there were no restrictions or no undefined points that we were looking at. So we can assume there's a nice clean turnover there. The domain of the exponential is all real numbers, so the range of my logarithm is all real numbers, and that's supported through the picture. The range of my exponential was 0 to infinity, so horizontal asymptote to infinity. The domain of my logarithm is vertical asymptote to infinity, which is 0 to infinity. So you can see the parallels there that we also saw with the relation tables when looking at domain and range for inverses. So that is still supported with this function. Not necessarily true for all functions that domain and range convert easily, because we have to look at, is the inverse even a function from the get-go, and some of the initial properties of the function. So some of the initial properties of the graph may dictate restrictions on domain for the inverse, but that is not the case here, so we can worry about that at another time. So we will conclude the video here. You have an introduction to the form of logarithms, their properties, things you should look out for, the constraints on the base, visuals, what growth versus decay looks like. Take note of the vertical asymptote that appears with the logarithm, as we already know about the horizontal asymptote that appears with the exponential. Know how the vertical asymptote moves, which we'll look at in another video. And then we did some log conversions between logarithmic and exponential form. You should be aware of that. And how to evaluate logarithms without the aid of a calculator. So we will end the video there. In the next video, we'll look at graphing logarithms, including transformations.